Welcome to section 10.3, hypothesis test for a population mean. Objective 1, test hypotheses about a mean. So recall, we use the student's t-distribution to construct confidence intervals for a population mean. Similarly, we use student's t-distribution to test hypotheses about a population mean. The logic behind the methods for testing hypotheses about a population mean is the same as it was for testing hypotheses about a population proportion. The connection is that just like when we use the t-distribution to build confidence intervals for means in Chapter 9, we'll be using the t-distribution to test hypotheses about means. So the concepts are parallel. So to test hypothesis regarding the population mean, we use the following steps, provided that the sample is obtained using a simple random sampling or from a randomized experiment. Sigma is unknown. The sample has no outliers, and the population from which the sample is drawn is normally distributed, or the sample size n is large, meaning n is greater than or equal to 30. And then the sample values are independent of each other. So why are these the requirements? Well, having a sample be obtained using simple random sampling or a randomized experiment avoids bias in the data collection. Sigma is unknown is important because in the real world, we almost never know the population standard deviation. So that's why we use the sample standard deviation S and the t-distribution instead of the z-distribution. For the third one, for small samples where n is less than or equal to 30, the data should come from a normal population and have no outliers. For large samples where n is greater than 30, the central limit theorem kicks in. So we're okay even if the population isn't perfectly normal. Okay, so it's important that our sample is normally distributed. And then the last one, independence. So each observation doesn't affect the others. So in these tests, the null hypothesis will be mu equals mu naught versus one of the three alternative hypotheses, where you have mu does not equal mu naught, mu is less than mu naught, or mu is greater than mu naught. Okay, so mu naught here represents the claimed value for the population mean. For example, if we claim that the average height is 65 inches, then mu naught would equal 65. Okay. So the procedure is robust, which means that minor departures from normality will not adversely affect the results of the test when performing these hypothesis tests. However, for small samples, if the data have outliers and the procedure should not be used. Look at normal probability plot to assess normality and a box plot to discover whether there are outliers. So if the normal probability plot indicates that the data does not come from a normal population, or if the box plot reveals outliers, then tests beyond the scope of this course should be performed. In translation, the t-test is going to be pretty forgiving, meaning it can handle data that's not perfectly normal, especially with large samples. But if you have outliers or severely non-normal data with a small sample, we would need to use different methods, which we won't cover in this course. So then what does robust mean in practice? It means that your data can be somewhat skewed and the test still works. It means that a few unusual values won't destroy your results unless you have very few data points. And that the larger your sample, the more forgiving the test becomes. Objective 2, understand the difference between statistical significance and practical significance. So results are statistically significant if the difference between the observed result and the statement made in the null hypothesis is unlikely to occur due to chance alone. So this means that if your p-value is small or less than alpha, you have statistical significance. This means the difference you observed probably didn't happen just by random luck. Think of it this way. If you flip a coin 100 times and get 75 heads, that's statistically significant. It's a very unlikely to happen by chance with a fair coin. So you'd have evidence that the coin is biased. Okay. So when a large sample size is used in a hypothesis test, the results could be statistically significant, even though the difference between the sample statistic and the mean stated in the null hypothesis may have no practical significance. So the problem with large samples is that with a huge sample size, you can detect even tiny, meaningless differences as statistically significant. Okay. So now let's understand practical significance. So practical significance refers to the idea that while small differences between the statistic and parameters stated in the null hypothesis are statistically significant, the difference may not be large enough to cause concern or be considered important. So this means that just because something is statistically significant doesn't mean it matters in the real world. Okay? So let's look at some examples. So according to the American Community Survey, the mean travel time to work in Collin County, Texas in 2008 was 27.3 minutes. The Department of Transportation reprogrammed all the traffic lights in Collin County in an attempt to reduce travel time. To determine if there is evidence that travel time has decreased as a result of the reprogramming, the Department of Transportation obtains a random sample of 2,500 commuters, records their travel time to work, and finds a sample mean of 27 minutes with a standard deviation of 8.5 minutes. Does this result suggest that travel time has decreased at the 0.05 level of significance? Their conclusion was that there is sufficient evidence to conclude that the mean travel time to work has decreased. So while the difference between 27 minutes and 27.3 minutes is statistically significant, is there a practical significance? In this case, the answer would be no. It has no practical meaning because an additional 0.3 minutes or 18 seconds isn't going to make anyone feel better about his or her commute time. So a 0.3 minute decrease is statistically significant because we have 2,500 people in our sample, giving us lots of power to detect even tiny differences. But it's not practically significant because saving 18 seconds on your commute doesn't actually improve your life in any meaningful way. So in this scenario, the huge sample size of 2,500 gave us so much statistical power that we could detect even this tiny difference. But with a smaller sample, we probably wouldn't have detected it. Okay, let's do another one. All right. So in 2003, the average age of a mother at the time of her first childbirth was 25.2. To determine if the average age has increased, a random sample of 1,200 mothers is taken and is found to have a sample mean age of 25.5 with a standard deviation of 4.8. Determine whether the mean age has increased using a significance level of 0.05. Their conclusion was that there is sufficient evidence to conclude that the mean age of a mother at the time of her first childbirth is greater than 25.2. So while the difference between the ages of 25.2 and 25.5 are statistically significant, is there a practical significance? Okay, and so we answer, Although we find the difference in age to be significant, there is really no practical significance of the 3.6 month age difference. So that's the 25.2 versus the 25.5 years old, which is a difference from about mid-March to the beginning of July. So yes, statistically, the average age increased, but practically speaking, a 3.6 months difference is negligible. So why did this happen? So again, in this problem, a very large sample, so we have 1,200 mothers, gave us the power to detect this small difference. But just because we can detect it doesn't mean that it matters. Okay. All right. So the bottom line on the difference between statistical and practical significance. You always ask yourself after getting a statistical significant result that yes, but does this actually matter in the real world? Is this difference big enough to change how we do things? Or would anyone actually notice this difference in practice? Okay. A big rule of thumb is be especially skeptical of practical significance when the sample sizes are very large. So n is greater than 1,000. The difference is statistically significant, but very small in magnitude. And the p-value is just barely below alpha. Okay, so those would be my tips for you. All right, and that concludes section 10.3.